Okay, let's get started today. All right, so this guy here, he's been doing his thing since last lecture, and he's really good at it right now. I guess I'll just let him keep at it. We'll see if he evolves by the end of the course. But in any case, his thing was reinforcement learning, and so we're going to keep talking about reinforcement learning today. So the first thing we're going to do is quickly recap where we're at, and I'm going to use that as a chance to show you some new demos. And then we're going to move on to thinking about how we can do reinforcement learning in bigger state spaces where, among other things, we can't just learn a Q value for every possible state and action pair. So remember the setup for reinforcement learning, which is the world this crawler lives in, is that there is a Markov decision process. So there's a set of states, and it's fully observable. You know what state you're in. Okay. There's a set of actions. Sometimes they depend on the state. And you know what actions are available to you. What you don't know is you don't know what the actions do. And formally that means you don't know, given a state S and action A, what S primes might result and with what probability. So you don't know the transition function. You also don't know the reward function. So you won't know whether a state action state prime triple is good or bad until you try it, until you experience it. The goal is to learn a policy, and formally a policy is a function from states to actions. Now, up till now, that's actually worked. We could have a table, like a hash map, that has states on one side and actions on the other side, but that's not going to work in a larger state space. So today we're going to have to figure out how we're going to be able to have policies when we don't get to have lookup tables the size of the state space. So in reinforcement learning, you don't know TNR, so you have to try stuff out. And the big idea in terms of the formal method of learning values and policies is to do everything we did with known MDPs, but to realize that mostly T was used to compute averages, to compute weighted averages. And we're going to compute those same weighted averages or expectations using samples. So in the process of doing this, we've learned a lot of different things. And I want to just make sure these are in the right boxes in your head before we move forward, because at this point, it's totally fair if you feel like you're swimming in values and Q values and stars and pies and Bellman equations and updates and iterations and who knows what's going on. So the reason why these things are also similar is there's really a small number of things going on, but they can kind of be combined in a bunch of different ways. Okay, so we started with known Markov decision processes where we would do an offline solution. So you know all of the terms in the MDP, and you're computing things like values and Q values. If you wanted the optimal values and Q values, we did value or policy iteration, and they're more or less the same algorithm, right? Policy iteration saves some time by not reconsidering actions at every step, but basically we did the value iteration update, which was the kind of core Bellman equation with a sum over T and also a max over the actions. So that's the core thing. Everything else is kind of a modification of that. So if we fix the policy, we can then do we get the same Bellman equations, except instead of maxes over actions, there's a fixed action pi. So the max goes away and a pi appears. And now the same algorithm, basically value iteration, where you fix the action instead of choosing the best, now has a new name of policy evaluation. The equations change, they have pi's in them, and we're still computing values and Q values, except now instead of the optimal values and Q values, we compute them for a specific policy pi. Okay, so those are the kind of key ideas on one axis, and the other axis that we've been seeing now is how do you mimic those same algorithms and those compute those same quantities when you don't know the MDP. Okay, last class we quickly talked about this idea of a model-based approach where you basically experience the world through experimentation, use that to learn an approximate transition and reward function, and then you reduce it to the known MDP case. That's not what most people do. What most people do is work with what's called model-free learning, which we spent most of last class and we'll spend all of this class on. So in model-free learning, you're doing the same things that you did when the MDP was known, in the sense that you're either evaluating a fixed policy pi, or you're computing optimal things. That's either learning the optimal policy pi star, or the optimal values or the optimal Q values. The techniques, though, are a little different. So the core method for a known MDP was value iteration. The core method for an unknown MDP is what's called Q-learning, which we'll recap right now, which you can think of as basically doing value iteration in a slightly shifted way. Okay, so in model-free learning, your information about the world comes to you through what are called episodes. So you experience a long sequence of state, action, reward, landing state S prime, then another action, another reward, another state, and you have these what are called transitions, a state, action, reward, landing state pair, and each time you see one of these transitions, you learn something. The idea in model-free learning is every time you experience a transition, you figure out where it goes in your Bellman equation, and you use it to do a little update that over time will mimic the entire Bellman update process from value iteration. Okay, so even though you have this whole string, you're really only ever learning from a single transition at a time, right? A transition from a state to the next state via an action and a reward. Okay, just a tiny bit more recap. We had an algorithm that we're going to extend today. It's called Q-learning. And I want to make sure this is really fresh because this is going to be the key thing we're going to use in order to attack larger state spaces. So we need to be really clear how it works in a small state space. So what we'd like to do is we'd like to learn the Q values for a state. We'd like to learn the Q values over time. And we could do this with a known MDP. And the way we would do it is we would do something much like value iteration, except it would be shifted, it would be out of phase. It would go from Q state to Q state in the expectmax tree. And the way we do that is we basically write out an unrolling of expectmax. It says the value of a Q state, and that K plus 1, remember, meant if you have K plus 1 more rewards before the game ends, the optimal thing you can get is a reward in the next step, right? So S and A are now fixed because we're at a Q step. So you get a reward based on your landing state S prime. Then you plug in your approximation to the future. And then you have to take an average of all those one-step look-aheads where the average reflects the transition function. Now, of course, we don't know the transition function, or for that matter, the rewards, so we're going to mimic this average. Okay, and remember, the key thing here is that it's an average over an instantaneous reward and a future, right? Where the instantaneous reward is real, right? You actually get it. It's the right value. And the future is an approximation that you've gotten so far. So as this algorithm runs, your future approximations are going to get better, and that's going to propagate backwards. Okay, you can't compute this, so what we do is we do it with these running averages. So the process is this. We receive a sample transition. Now, we talked a lot about how you decide what action to take. Q-learning doesn't care, right? Q-learning has an update that it does, and there's a separate module which kind of thinks deeply about what action should be taken next. Okay? So you receive a transition, which is a state, action, reward, and S prime. And what you do is you go through this following argument. And we're going to have to repeat this argument later in a different context, so let's make sure we're clear on it. If this sample were the only thing that can happen from this Q state, meaning there's no other S prime that's possible, then we have evidence that the score we're going to get from this Q state is the reward we just received just this instant, plus our current approximation to the future value of Vs. Okay, now that's the value of Vs prime here. What is that? Well, we're doing Q-learning, so we have to kind of synthesize the value on the spot, and we do that by taking a max over actions of the Q values that come out of S prime. Okay, so we synthesize V kind of on the fly in this equation right here. All right, so right now our current sample says instantaneous reward plus future approximation. We look at that, but then on the other hand, we have this past evidence that we want to average into because our past evidence reflects other S primes that can happen. And we need to be computing an expectation and not just clobbering our data with each sample that comes in. So we keep a kind of running average, and this is one way to write it, where the new value of the Q value is mostly the old value. So alpha is something like 0.1 or 0.01. It's mostly the old value, plus a little bit of this new sample blended in, right? And as we do this over and over and over, the new samples slowly accumulate to form an average. And as we talked about last time, it's not an even average. The newer samples always have more influence, and that's actually a feature, not a bug. The reason why you want the newer samples to contribute more is because each sample contains, part of the information in each sample is this plugged-in approximation, and that's getting better over time. So newer samples are actually more accurate. And so, you know, we look at this running update, and we see that it's more or less going to give us this effect. And so this is the basic version of the algorithm. Okay, so I'm going to give you a demo, and then we'll talk about the properties of this and how to extend it. So here is a new grid. Maybe I'll do it by hand first. So here's a grid. And imagine you're doing Q-learning. Okay, you know what the states are, and you know from each state there's north, south, east, and west, except for some of the states you only have the action exit. And you look, and everything is 0, right? Because you don't know anything yet. So how do I know what things are? Well, maybe if I go south, that's good. So I try it, right? And it still seems fine, and then I choose exit, and okay, that was bad. All right, so we know that's bad, but we don't know maybe if we go over here and go north, and maybe that's good. Okay, that's bad too. And so I have to try a lot of things. And, oh, that one wasn't so bad. Maybe I'll go over here, and I'll go out here. So we learn about things as we try them. And I'm going to spend some time kind of just walking right here. And as you can see, right now from this position, I'm about to move into a square when I choose the east action. I'm going to move into a square that has a positive Q value for one of its actions. And so we take the max. The value of my landing square is going to be 2.5. That means the 0 Q value for going right from here is going to increase, right? How much it increases, okay, it looks like we have a learning rate of like 0.5 now. All right, so I'm just going to do this for a while so that we can prove another point. Yep? Are you asking why it changed from a bright green to a dark green, or why the number changed from 0 to 0.5? Yeah, so at the time it was the best value, and the colors are all normalized to the values on the board. So when we found something better, it didn't look so good. That's just the GUI. There was nothing in the algorithm about that. Okay, any other questions? That was a good question. All right, so I'm just gonna kind of pave this path. And so as I do this, first of all, notice a ton of things are still 0 because I've never tried them. Like, I don't know what happens if I go left from here. Now, if I go left, what's going to change? This number is going to change because that's the Q value corresponding to what I just did. And when I land to the left, how good is the state I land in? What's its value? Okay, ignoring discount, it's 6.23. So that 0 should go up, and so I'm going to try going left here. That 0 should go up. To what? If the learning rate is about 1/2. It should go up to like 3. And there you go. So I could just like go back and forth maniacally here just to convince this that these two states are connected, and they'll slowly equalize, right? So you learn about what you do. Now here's the point I was building up to. We've learned something about this kind of long sequence, right, of going to the right, and we know it's worth, as far as we know right now, something like 6.74. That's partially because the learning rate still hasn't caught up with the real values, and it's partially because there's a little bit of a discount maybe at play. We'd have to look at the exact parameters. Now I'm going to start doing dumb things, right? So here, let me just maniacally go back and forth here to get these all more or less learned to something reasonable. Ugh. All right, I'll show you a different way. How about that? Let's look. It's just going to run on its own. Okay. So here you see it's a slightly different board. It's discovering that there's a good exit and then a whole bunch of bad exits. And the interesting thing is it's jumping off the cliff a lot. Why? Well, there's actually an exploration policy here, and it's moving random at a certain fraction of the time. And even though, let me grab this before anything bad happens here. Okay, so if you look at the start state, which is the middle left thing, okay, if you look at the middle left thing, what is the current value of the middle left thing? Okay, there are 4 Q values. The value of that state is the max of them. So currently we would say 9.59, right? So almost 10. So the value of that start state over in the middle on the left is almost 10. That's because if you act optimally, meaning you don't jump off the cliff as you go rightward, then you'll get a 10. Now, this agent that's been acting almost never does that successfully. Usually it decides to jump off the cliff for science at some point along the way. Okay, and what that means is we haven't actually experienced that 10 as our average. But Q-learning doesn't record the Q value that you achieve. It learns the Q value under optimal play. So even though if you watch this thing and it's often just doing kind of crazy stuff, we're still learning the values that we would achieve if we act optimally, even though we're not acting optimally. The second thing you can learn here, The second thing you can learn here is that we are learning that going south from this bottom row is bad. But that's a statement about the Q state where you go south, not about the state itself. The state isn't somehow tainted by the fact that there's a stupid thing you can do. The value of each state is determined by the thing you should do. Okay, so we'll let that run for a little bit. And you can see actually another effect here, is that there's some things that we just haven't been doing under this exploration policy. So there's some randomness. Sooner or later, we'll get to the top right corner, and we'll try the north action. And we'll figure out that it's actually not that bad, because as long as you go south after that, you'll get a lot of points. But when we tried it one time, we landed in some state that at the time wasn't very good, and we haven't been back since. So this exploration function just never makes it back there. And actually, it's kind of hard to get to that state, because you have to kind of not jump off the cliff and not go into the good exit, and you have to make it all the way up there without bouncing back out, and so on. And so we're not kind of learning equal amounts everywhere. We're only learning about the things we do, and at some point, that's actually reasonable. We want to start doing the things that look good and not the things that we think are kind of mediocre, but we're not sure exactly how bad. Now, if we were going to play this game forever, we would want to eventually kind of learn everything about everything just to be sure. But at the moment, okay, I'm going to stop it again. Okay, here's another thing. We know exactly how to act, right? In fact, you can see from these values, there must be a living reward of minus 0.1. There's no decay in this case. And what we should do is we should move immediately rightward. So we should just go right, and then take the exit. We no longer have to be jumping off the cliffs. Like, look at those numbers, minus 99.98. Okay, we've got it. We don't have to keep doing it. But this exploration policy keeps doing it, because that's how action selection is working. It's saying do the thing that the Q values suggest 80% of the time, and 20% of the time do something else. And in that start state, we know what all the directions do. We should not be being random at this point. Okay, so if you act optimally, you're going to get a 10. Any questions on this while it finishes out? Because I'll have one more point at the end. Yep. So the question is, when it's 20% time to do something else, this one has the simplest possible algorithm. It picks an action at random, which may well be the action it would have done if it was exploiting. Okay. Yes. You mean, why don't we reach the terminal state of the game?
No,
the bottom right. Yeah, okay, so the reason you can't get to the bottom right is because there's no action, there's no Q state that leads there, right? You can't get there. The closest you can kind of get is into one of the exit states next to it, which don't lead there. They lead up or wherever. Yeah, the rules of this grid world, yeah, I mean, it's important to separate what's the rules of this grid world from what's MDPs in general. In this grid world, you have to exit from the exits. Yes? How can the squares in the second row be minus 0.2? Why is the Q state example for here, so how come the Q value for going south is 9.7? Yeah, actually going south from the middle square is worse than minus 100, because not only are you going to get stuck with minus 100 later, you're going to get stuck with minus 0.1 immediately, because this grid world, unlike some of the other demos, has a living penalty of 0.1. So yeah, the only thing worse than being in the bad exit is being forced to soon be in the bad exit. All right, so we're going to let this run. I'm hoping it will eventually stop. All right. If we get to 400 and it doesn't stop, I'm going to give up. Any other questions? Okay, we're just going to stop. Oh, now there's a question. Okay. That's right. You can't actually get to that square in the rules of the game. Okay, now, here's the point. The point is if I go back up and, so close, it probably was going to stop forward. Anyway, if I look at all of these returns, I'm going to make a number up. So if I look, we know that the Q value of the start state, the value of the start state, meaning maxing over the Q values, is 10, right? Or something like 10, 9 point something. But if I average together all the returns that I get, it's going to be pretty bad, right? Because most of the time I end up falling into a pit because of my exploration. So I might average up all of my experiences in this grid world and say, all right, what have I determined? I've determined that the value of the start state is plus 10, but my average returns from the start state are like minus 40, right? Because I'm getting all these negative 100s in the mix. And what that proves, the average of the returns you get, okay, that's an approximation to the value under your policy, which has exploration in it. But the Q values you learn in Q-learning do not reflect that. They're values, approximations to the optimal values. Okay, this is why Q-learning is what's called off-policy learning. The numbers you fill in the algorithm are not the values of what you're doing. They're the values of what you should be doing, the optimal policy. Okay. Any other Q-learning questions before we move on? Yep. Q-learning stretch. Question? Okay, so you're asking why would the start state actually get to 9.6 or something? And the answer is that's the best you can do. You have to take a couple hits before you get to the exit. If the living reward was 0, then it would be 10 everywhere except for the actions that force you into a bad exit. Good questions. Yep. Yes, so there are alternate formulations of grid world where you receive your reward upon entering a state. So if you enter the exit, if you enter one of these squared states, but this is the one that we have. We use the grid world we have. You can make up your own grid world if you want. Okay, any other questions? All right, let's stop that now. All right. Okay. So moving on. All right, we talked last time about exploration versus exploitation. Okay, the idea I think we covered pretty well, so I'm not going to go through that again. But we're going to talk about how you achieve exploration because we did that really quickly at the end. So you always have this decision between doing things that you know are good and things that you don't know but might be good. Okay, and what you just saw was what's called an epsilon greedy exploration policy. So the blue dot was doing what the Q value suggested most of the time, and with probability epsilon, it would take a random action. Now there's a couple reasons why this is bad, and we saw them all in the demo. One reason it's bad is at some point you know what's going on, and you should stop doing exploration, right? You only explore while there's knowledge to be had. So one thing is, you know, over time you want to explore less. Now you could make that happen. You could lower epsilon to 0 according to some schedule, and that would be a little bit better. The other problem is that when you do explore, you know, we saw that it was over and over again, even when there were unexplored areas of the grid, we saw that it would be jumping off the cliff, which it already knew it was bad, whereas what it really should have been doing is trying to find a way to get to the upper right because it didn't know much about that region. And one way you can do that is what's called an exploration function. And we saw the crawler learn very quickly on this, but the basic idea is this. When should you explore? Not randomly, but what you should do is somehow have a way of knowing that the good actions to take, partly an action can be good because its Q value is high, but partly an action can be good because you don't know what it does, or because it leads to an area whose value you don't know. Okay, and one way to do that is to, instead of being random, is to basically charge into the unknown. Okay, and as you can see from the drawing here, charging into the unknown is often a very bad idea. So you're going to incur some losses when you do this. There was a very good question last time about what would happen if, for example, you had a grid world which looked something like this. Like, what if your grid world was kind of a plus 10 and it was surrounded by kind of a moat of minus 100 or something like that. Maybe this is plus 10 million to make it worth it. Okay, so there's this really good prize in the middle, and then there's a moat around it and then a whole bunch of zeros out here in terms of the rewards, not the values. These are rewards. Okay, and so if you were a poor little robot kind of out here, and you had to explore, you would kind of bounce around, you'd see a lot of zeros, you'd try out the moat, and it would be bad, right? And eventually you would just know that all of these squares are bad. And you wouldn't know what was in the center, but you would kind of know there was no safe way to get there. Okay, and it might be that you would never find the thing in the middle. But as as an agent, you don't know the difference between a moat that is the kind of a ring of fire where inside is a gem and a ring of fire where inside is more fire, right? You don't actually know the difference. Okay, and so you can imagine what does epsilon greedy do? Every now and then you'll kind of bounce around, which means sooner or later you're eventually going to try everything, but it might take a while. And you might spend a lot of time bouncing in and out of the moat. What's an exploration function going to do? Let's take a look. So an exploration function, here's one way to do it. This isn't like, there's nothing provably optimal about this exploration function. It's just to give you a flavor. You have a function which takes a utility, that's a Q value, that's a score, and a count of how many times you have visited this Q state. Okay, and it says, well, the exploration value is the utility plus some constant, which might be big or small, divided by n. So as n goes to infinity, this converges over, this in the limit goes towards the utility, but at the beginning it gets a boost. How much of a boost? It depends on k. All right, so what you can do is instead of doing your Q update, where you consider the future of what you experience to be its actual value, right? You say, oh, I landed in this state and it looks like it's worth 0. Well, maybe it looks like it's worth 0 because you've never been there. So what you do is you change this part, the evaluation function part of the Q update, to use the exploration function of the Q value and the number of times you visit it. So now, whenever you take an action and it takes you somewhere which might in fact be bad, but you don't have a lot of information about, it's going to look good to you. So this function makes everything look good if you haven't been there very many times. And if k is very large, then kind of the biggest way to increase your values is to go places you've never been. Okay, so if you crank k up, you're going to just explore, and you might go straight through that moat because k's bigger than the pain of the fire. But if k's not that big, right, if you're not supposed to do that much exploration, there might just be parts of the world you never get to. So these are the kinds of things you can worry about in practice. And if you think about it, imagine you were in a giant infinite casino, and there were all of these slot machines, and each one had a different payoff. And you had, if there were 30 slot machines, and each one had a different payoff, and you had infinite time, you would try them all. And even the ones that were kind of unlucky, maybe try them less, but you would eventually try everything so many times that you would discover the best thing, even if you were just unlucky in your first couple trials. Right, so when you have infinite time and a small number of options, sooner or later you sort everything out. But what if you're kind of in a nearly infinite casino, and you've only got 15 times you can pull the lever, and you pull the first one and you lose, and you pull the second one and money comes flying out, right? Maybe you never try the third one. Maybe you don't try 15 different things. Maybe you double down, and if you're trying the second one and it's working pretty well, for all you know, the 312th one's even better, okay? But if you don't have enough time to try everything, there's no guarantee that you can actually ever converge to the optimal thing. All of this notion of converging to optimal things is when you can keep trying things over and over again until you can kind of squash out all of your uncertainty. Okay, any questions on that? Let's start here. Yeah, so this function, if you think about what it does, whenever you update a Q value, you, instead of saying my new sample on this Q value is the reward I achieved plus the kind of unbiased goodness of the landing state, I say it's the reward I achieved plus the unbiased goodness of the landing state plus a reward if this action took me someplace I don't know much about. Okay, but it will never get you to the lower right corner. It is, but you can't teleport, right? All the exploration function does is it gives boost to Q values to the extent that they have recently been taking you to some place that has a high value, or rather a high kind of exploration augmented value. Yep. Is there a way to know what k should be? So, I mean, the short answer to all of these things is no. It's very hard to know what the optimal thing is, but of course, in practice, there would be ways to do it. So you could, if you had a bunch of trials, you could try different values of k on different boards and say, for the distribution of boards that I'm sampling from, this value of k works on average. You can use the same kinds of techniques that we're going to talk about when we get to machine learning to try to do it in a data-driven approach, but there's no kind of great theory that says, in a tractable way, here's how you explore. There is actually a great deal of math worked out about what in principle is the tree computation that gives you the optimal exploration. But unless you're dealing with very trivial cases of like simple slot machines or something, it's very hard. Like in the exact case of you have slot machines and you have a very particular kind of belief about how they work, you can actually compute what you should pool in a way that kind of optimally balances exploration and exploitation. It's something called a Gittins index. But in the general case, this is totally intractable. I mean, welcome to like CS 188. AI is totally intractable. We do our best. Was there another question? Yep. In this exploration function, as I've written it here, there's no randomness. But whatever you do, kind of, you become disillusioned with, right? Just by doing it, you make it worse. And so sooner or later, something else will win. Okay. All right. Last point, which we also saw, is this notion of regret that I keep alluding to, which is that, you know, you have this robot, and how did it get to be the old wizened robot? It made some mistakes in its youth, right? Just like everyone. And we can talk about two things. We can talk about, does it know the optimal policy? This robot apparently knows the optimal policy. Okay, that's a good thing. Knowing the optimal policy is a good thing. But there's also, we were learning the optimal policy in that demo that I showed at the beginning, but once we knew the optimal policy, we're still like flinging ourselves off the cliff at kind of random intervals, okay? And so there's a difference between the policy that you learn and the losses you incur along the way to learn it. And in that case where you're in this kind of infinite set of slot machines, maybe what you really care about isn't learning the optimal thing because you're not going to play for that long. It's kind of not losing too much while you're actually playing. And so this is a different concept. This is about the losses you get not after learning, but during learning, okay? And this notion is regret. Regret is the measure of the kind of total cost of mistakes. It's with the appropriate averages stuck in, it's the difference between the rewards you get, including all of your exploration and mistakes and bad luck, and the optimal thing, okay? So if you want to, so you can't actually drive regret to zero in general because you're going to make mistakes and you have to explore. Okay, the only way to have zero regret really is to know the optimal policy. But we can talk about different algorithms having more or less regret, even if they're both optimal. So as we saw, Q-learning for basically any exploration policy that eventually tries everything will converge to the optimal values and policies, but some have higher regret than others. So the epsilon greedy thing that's just kind of bouncing around at random, it's going to be optimal in the end, but it doesn't optimally learn to be optimal. It's going to have high regret along the way to becoming optimal, whereas an exploration function might have lower regret along the way. Questions on that? Okay. All right. So now what we're going to do is we're going to talk about how this is all going to work in the context of an MDP like Pac-Man. Right, you maybe didn't think about Pac-Man as an MDP. Where's the uncertainty in Pac-Man come from? It comes from what the ghosts do, right? Pac-Man acts, the world responds with a configuration of ghosts, and then you act again, okay? So how are we going to deal with these large states? And the answer is going to be, we're not going to have a big lookup table anymore. We're instead going to learn about properties of states in a way that's going to be very reminiscent of your project too, okay? So how does basic Q-learning work? You keep a table of all your Q values. So when I run that GUI with grid world, each cell is a number, and that's our knowledge. Our knowledge is this list of real numbers for each Q state. So you can imagine you've got this book, and it tells you for each state there's a lookup value, and you kind of once you've filled this book in, you're done. Okay. In realistic situations, this just isn't going to work. Okay. So we're not going to be able to learn about every single state. Why not? Well, it takes too long to visit every state of Pac-Man. Think about all the board configurations. You can't possibly visit them all, even if you only had to visit them once. Secondly, even if you could visit them all, right, you would have to store your knowledge somewhere. So you would need memory that was proportional to the number of states. That's bad. And it's actually worse than that, right? Because even if you had the time and memory to visit every state, you can't actually, it's not trivial to figure out how to get to states. This is back to that issue of that state you couldn't get to. You may want to go to that state, but how do you get there? You need to kind of know how to play the game in order to even do that. So there's a lot of reasons, but the short answer is the state space size is too big. So if you imagine the lookup table for Pac-Man, this is like a whole library full of Pac-Man states. And if you want to know what the value for your current state is, you need to like find it in there somewhere, and that's just not going to work. So let's actually take a look at Pac-Man reinforcement learning. So here is, let's try, this is going to be Pac-Man reinforcement learning. What does that mean? It means somewhere that you can't see, because this isn't grid world. And if it's not grid world, I can't show you the Q states very well. But in Pac-Man, what's a Q state? It's a picture of the board with a direction that you're about to move. That's a Q state. So somewhere in memory is every configuration of the board, every direction you're about to move, and a number that starts out at 0. And we're going to play game after game after game, and slowly learn that some states are better than some Q states are better than others, which will teach us how to act. So let's watch reinforcement learning Pac-Man. And the reward, by the way, is just the change in score. So when you die, you get a big negative reward. When you eat a dot, you get a positive reward. Okay, so here we go. Okay, you lose a lot of Pac-Man this way. So what's Pac-Man doing? Maybe I'll go left. Maybe I'll stop. Maybe I'll go left. Look, he ate the dot. Good. Okay, death, death, death. Okay. And you say, why doesn't he eat the dot? He has no idea that going south produces a reward, right? You're thinking like search. You're thinking that you know the model and you can think about the consequence of your actions. Pac-Man is just kind of learning over and over again all the different ways you can die, right? It's actually quite grim. Okay, so we could do this for a long time, and you can see he's slowly starting to figure it out. We're winning more now. Occasionally we're going to get some bad behavior. Okay, you can see it's kind of working, right? You know, it's not generalizing all that fast, but sooner or later you kind of experience everything. How come we experience everything? Because it's just not a very big board. Okay, so now this will work. Okay, so if I'm going to have it train in the background. So you can see here it's training it's going to train 2,000 episodes, and you can see the average scores are going up from negative to now it always wins. Okay, so this Pac-Man plays really well. There's no minimax search or anything like that going on. We know for every single configuration of the world whether it's good or bad, and we're using that to play optimally. So it's optimal. It's just not the most efficient thing in the world. Okay, in terms of learning. Statistically efficient. Okay, so what happens if we go to a slightly bigger space, like this one? Okay, first of all, we're going to spend a lot of time thrashing around before we even discover that there's a dot. Okay. I won't put you through the whole thing, but here we're going to train. Now watch the kind of average. Minus 500 is our average over 100 episodes, minus 400. These 100 episodes, minus 300. Okay, we're doing better. We're still losing a lot, right? But every kind of batch of 100 episodes that we play, we're getting a little bit better. So we've played 800 times. We still usually lose, but we're slowly working our way up. Okay, 1,100, 1,200. It's taking a little longer because the episodes are a little longer. Why are they longer? Because Pac-Man's sitting there having no idea what's going on. The ghost is bouncing around randomly, and it's going to wait for sooner or later for someone to accidentally do something right. Okay, so we're about to be done, and now we'll see Pac-Man play. So, of course, this can eventually work. Oh, except he's playing back there. Okay, this is the board we were on this time. So, it's not like, occasionally he'll twitch around, but he's basically playing the game. Okay, so you can imagine that this would scale kind of badly to very large Pac-Man games. Okay, so we're going to fix that right now. So what you really like is you'd like to learn about some small number of training states from your experience. So you try a small number of things, you're going to learn about those, and you're going to generalize to other things that you haven't seen. Right? You want to do things like, once you learn that one ghost is bad, you learn that really having the ghost hit you from in any square might be bad. Okay, there was a question. Right, so the ghost is part of the state. So it has to learn separately that if the ghost is to your right and you don't move left, you're going to get a big negative reward. And it has to learn that for every single square. And you have these intermediate states where it knows that for 80% of the locations. And so it'll avoid the ghost, and then it'll get to some position. It's like, oh, I don't know what happens when the ghost gets me here, and it'll stop. Right? And so you have to kind of exhaustively learn about every single thing, and that's why it's inefficient. But eventually it will work. I mean, this stuff works in the limit. It's just not practical in a lot of cases. Okay, so what we're going to do now, we'll actually take our break now, but then when we come back, we're going to figure out how to set up Q-learning in such a way that when you have an experience about one state, it teaches you about other states that are similar. Okay. All right, let's start again. We're going to figure out how we can get reinforcement learning to work in a case like Pac-Man. And what it really has to do with is generalization. So let's say we're playing Pac-Man on a board like this, and we have a bad time. So we get this big negative reward. What do we learn? We learn this state is bad. That's what reinforcement learning is supposed to do. You have a bad experience in a state, and you learn that it's bad. And it does a little bit more than that, because we'll slowly propagate these things backwards too. We'll also eventually learn that states that lead to the state are bad. Okay, but let's just say that we learn that this state is bad. In the naive version, right, where you just have a lookup table that maps states to values, you're not going to actually know anything about this state, right? This is also bad. You and I look at this and we know this state's bad too. But what you learn from the state on the left doesn't transfer because this is a different state. You also don't know anything about this state. Why not? There's a dot missing somewhere, right? The dot has nothing to do with the situation, right? But it's enough to make it a different state. So you can see what the problem is. The problem is what you're learning about when you have a bad experience on the left is you're learning that it's bad to be pinned in by two ghosts, okay? Maybe it has to do with exactly what your local configuration is as far as the maze. It certainly doesn't have to do with kind of whether or not the dots are eaten or not in the upper right corner, okay? And so we'd like to somehow compartmentalize our learning to the aspect of the state that actually was relevant, okay? And this is going to be the solution. The solution is going to be feature-based representations. So what we're going to do is describe a state, not as kind of a specific entry in a table. A state is going to be described using a vector of numbers. These numbers are called features, or you can think about them as properties. What a feature is, formally, is a function that maps a state to some real number. Often that's either 0 or 1, meaning usually true or false. And the idea here is these functions, or these numbers, capture important properties of the state. So what features might characterize a Pac-Man board? Well, maybe you have a feature that says, how far am I from the closest ghost, right? Different states might share this feature value if they're similar in terms of ghost proximity. You could have one that's distance to the closest dot, or the number of ghosts, right? Or maybe 1 divided by the distance to the dot squared, or something like that, so that it's better to have this feature be large. It means you're getting close to the dot. You could have features like, is Pac-Man in a tunnel? Maybe you want to learn that ghosts are more dangerous when you're in a tunnel. Okay, and so you could imagine, really spend a whole lot of time imagining features that take a board and compute some number that reflects some aspect of that board that might cause it to be a good or a bad board. And so what we're going to do is we're going to, as humans, the way this is going to work is we're going to come up with the features, right? We're going to do what's called the feature engineering. And then the reinforcement learning is going to learn for each feature what it means for the value of the state. And so we're going to learn about each feature rather than learning about each state. And there's not going to be that many features, and so this will be more efficient. Okay, we talked just now as if features are properties of states. If we're doing Q-learning, they're technically going to be properties of Q states, like, does this action move me closer to food? Question? Yeah, good question. The question is there any way to automatically come up with features? There are, but the technology for taking a set of features and weighting them in some optimal way is much more reliable and kind of much easier to use than the technologies that do feature induction. There's a variety of ways you might do it. So sometimes people start with primitive features and automatically explore the spaces of conjunctions with them. There are other techniques. This is one of the advantages that people claim for neural net methods, is that they're able to kind of combine primitive inputs into something that looks a little bit like a soft conjunction. And so there are ways to do that. And we will come back to that later in the course, but mostly for now, we're going to imagine that the features are set. Some might be maybe useless. You may have over-generated. But in there somewhere are some good features, and we're going to learn how to pick them out and weight them. Good question. Other questions? Okay. What are we going to do with the features? Well, features are great. They're vectors. But values, or Q-values, are real numbers. And so essentially, we're going to say each feature has a weight, and we're going to take the dot product of these two vectors. So we're going to sum up each feature times its weight. And we're going to say that is my value or Q-value. So this is a linear approximation to the values or the Q-values, where the features are fixed. They're constants. And what can be learned is the various weights you give them. Okay? So what's the advantage of this? The advantage of this is that everything you've learned about playing Pac-Man is summed up in the knowledge that ghosts are bad and dots are good, right? You don't have to learn about each state. But on the other hand, you may have states that are very similar in terms of their feature representation, but totally different. For example, if you have some features that look at kind of proximity to ghosts, right, there's a big difference in Pac-Man between kind of this state, where you've got two close ghosts, and this state here, where the ghosts are on both sides, right? Both of them might have similar feature representations if your features are just how close are the ghosts, how many ghosts are there, but one's much worse. So the danger is if states with the same features are different in value, there's just no way you can have a good approximation. And there's the trade-off there. Okay, you would like to have this be lower dimensional, but sometimes then you mess up and things that are very different start looking the same. All right, this here, this kind of value of a state is weights times features added up. We've seen this equation before. When did we see this? We saw this in Project 2, right? We saw this when we did depth-limited minimax search. And when we got to the bottom, we would plug in a number which came from features and weights all added up. This is exactly that, except now we're learning the weights. Okay. So let's take a look. How does approximate Q-learning going to work? Well, we're still computing values of Q states. So we're still computing Q values. That means you show me a state S and an action A, and I still have to produce a number. I'm just not going to go to a lookup table. What am I going to do instead? I'm going to look at the Q state, and I'm going to compute its features. How many ghosts? Am I moving towards a dot? Whatever I'm going to compute. I compute all the features, and then I take my weights, which have been learned, okay? And then I multiply them together. So that's the recipe that gives me a Q value, and learning is going to be setting the weights, okay? So how are we going to do learning? It's going to work like this. A transition is going to come in. So the transition says, you were in state S, your action selection policy chose action A, you received reward R, and you landed in S prime. Now, what are you going to do? Well, in standard Q-learning, what we did is we said, we did it a slightly different way, but basically what we did is we said, there is a difference here between what I thought I was going to get from the Q state SA and what I appear to be getting now, which is the reward I just got plus the approximate value of the landing state. Okay, and we wrote this a little differently, but what we do is for the transitions in classic Q-learning, we compute the difference. Does it look like I'm going to get something here that's better than my old value or worse than my old value? And then I modify my Q values. So this is a slightly different form as we saw last time, but it's mathematically equivalent. And it says that you compute the difference between what you thought you were going to get in your kind of approximation to date and what it looks like you're going to get now. And then you nudge the Q value for that Q state in the direction that's appropriate for that difference. Okay, so if it looks like your Q value is too low, you raise your Q value. And that's how learning happens when the Qs were exact, when we had a lookup table. Except now we can't do that. We have some experience, and we're like, wow, this Q state is much worse than I thought. We can't just lower the Q value anymore because there's no entry for it. What we have to do is lower feature values. And so what we do now is we go through and we look at each weight and we nudge it in the appropriate direction. And I'll derive in a second why it takes this form, but we basically nudge the weights. That's the difference. When we have an experience, we adjust the weights in the way that's appropriate rather than changing the Q values directly. So here's the intuitive I will both show an example and then I'll derive this update, but let's just do the intuition right now. The intuition is whichever features were active in this state, right, we're going to learn something about. So if this was a state where a ghost was next to me and it was bad, I'm going to learn that the feature ghost next to me contributes negatively to the value. Okay, so if something unexpectedly bad happens, we allocate blame. Now, which features should we blame? Well, we should blame the features that are on. And so that's why we have to have the feature value in this term. So to parse this visually, we update each weight I. So for each feature I, we update its weight. We start with the current value. We nudge it in the same direction as before, the direction that will make our error less. And we scale each weight by whether or not that feature is there. So if the feature is 0, moving its weight around is not going to help. Okay? And if the feature is positive, then we want to make sure our update is positive. And if the feature is negative, we want to make sure it's negative. And multiplying by the feature value does that. Okay, let's see an example. And then we're going to formally justify this from a least squares perspective. Okay, so here's an example. This is Q-learning for Pac-Man. So let's say our Q function is as follows. You give me a state action pair SA, and I'm going to compute two feature functions. One feature function is going to be 1 over the distance to the closest dot. How am I going to know that? I might have to do some search. Doesn't matter, right? 1 over the distance to the closest dot. The other function I'm going to get is 1 over the distance to the closest ghost. And then what I'm going to do is 4 times the reciprocal dot distance minus 1 times the reciprocal ghost distance. And that's going to be my Q value. Are those the right Q values? Probably not. Okay, but that's my function. So let's see how it's going to work. I'm in some state. Okay, so here's the state where I'm kind of pinned in and things are actually going to go badly. And in this state, the reciprocal dot distance is 0.5 because there's a dot 2 away from me. And the reciprocal ghost distance is 1, okay, because there's a ghost that's 1 away from me. So the Q value, according to this recipe, is plus 1, right? 4 times 0.5 minus 1 times 1. All right, so far so good. I take the action north. What happens? Badness happens. So I take the action north, I experience the reward minus 500, and I land in the terminal state where the game is over. Okay? By definition, the terminal state has kind of all of its Q values to 0. So let's walk through that update. So we're going to do the same logic as before. Our current prediction of the Q value was plus 1 for this state S on the left. What was our experience this time? Well, it was a negative reward, right, minus 500, plus we plug in the value of the landing state, and the value of the landing state is 0, okay, because it's the end. So we look. On one hand, we thought we were going to get plus 1. It looks like now we're going to get negative 500, and so our Q values are way too high. We need to lower the Q value. How are we going to lower the Q value? Well, we take this difference, which is about minus 500, and we do the updates. So each of the weights, which are 4 and minus 1 at the moment, is going to get adjusted. And it's going to get adjusted in proportion to the following things. The size of the error, right? The more off we are, the more we need to change the weights. The size of the feature, right? The ghost was closer than the dot, so it's contributing more to the function, so we're going to adjust it more. And then alpha, which is some learning rate. Okay. This is not exactly the other alpha, but it kind of does the same thing. All right, so what do we do? Well, it depends on the actual value of alpha, but kind of if we set alpha to the right thing, then what's going to happen? We're going to lower, right? We're lowering weights, right? Because we had a bad experience. So the reciprocal dot weight goes from 4 to 3. Okay, being near a dot isn't as good as we thought. And the reciprocal ghost weight goes from minus 1 to minus 3. It changes more because its feature was more active. Okay, are these Q values right? Probably not, but they've moved in a reasonable direction. If we look back at the Q value for this state, it's going to be lower now. Does that make sense? So we have an experience, we allocate the experience to the weights, and now we have a new function. Okay, let me show you that. Let me show you that in the demo. Okay, so what we're going to see now is, this is reinforcement learning. This is still your project 3s. You're going to see Pac-Man play a game, except instead of being a tiny little game, it's going to be a real game on a reasonable board with some ghosts in the mix. And what's going to happen is, after every step, it's going to do a Q update. But the Q update is not going to be a table update. It's going to be a weight update. So the features have to do with how close the ghosts are, how close the dots are, and so on. And so as soon as it eats its very first dot, it's going to learn that dots are good. Any state that has dots close by is going to get a boost from that. So eating a single dot teaches you about, okay, essentially all you need to know about dots. Now, you probably don't have exactly the right weight, but you learn something positive about dots. And a single death at the hands of a ghost is going to teach you that ghosts are bad. Okay, so let's watch what happens and see if it learns faster than the kind of thrashing around thing that happened before where it took us forever to learn. So, single game. Okay, it's already learned that dots are good. Okay, now it knows ghosts are bad. Okay. Now it really knows ghosts are bad. So, we learn a lot faster. That's it. That's all you have to learn, really, to play Pac-Man kind of okay, is that dots are good and ghosts are bad, right? So it shouldn't be too surprising that you're able to do reasonably well. But, compared to what we saw before, this is much faster generalization. It's not perfect. Okay, now it's not eating the power pellets, right? Why not? Well, partly it's never done it, so it has no reason to know it's good. And secondly, I think in this case, the features don't have it, and if the features don't have it, even if it accidentally does it, it won't be able to learn that it's good to do. By the way, no minimax going on. This is just a reflex agent. Okay, so pretty good. You'll get to build that. Okay, any questions on that before I motivate why this update is the way it is? Okay. Okay, so how many of you have seen linear regression in some context? Okay, so now you know where the Q-learning update comes from. It's basically just linear regression. So what's linear regression do? Linear regression says I have a bunch of points, and I have a family of lines that I can choose, and I like to somehow find the best line, the one that fits best. How? Well, I define some notion of error, and I choose a line that minimizes that error. This, by the way, is exactly how machine learning is going to work later. So this will also be a preview of the ideas that go into machine learning. So let's say I was doing regression, right? Nothing to do with reinforcement learning, nothing to do with Pac-Man. I just have a bunch of data in a spreadsheet, and I have each data point we'll call x. Okay, so what are the features? Well, typically these data points in regression are they're just a sequence of numbers, and so each feature might just be a different coordinate in the vector. Okay, but that doesn't matter. F1 is the first entry of the feature vector, and F2 will be the second. And if I wanted to do a one-dimensional linear regression, I would say I'm predicting y's. I'm doing them for each point x on the basis of F1 of x, which is some number. That's the first coordinate. And I have a family of linear functions. Okay, I can change W0, the intercept term. I can change W1, the weighting on the first feature. And as I do that, this line moves around. So what do I want? Right? I would like to somehow fit those points. Okay, if I have 2 dimensions, now I'm kind of putting a plane in that matches these points as well as possible, and now I've got 2 features. And as I add more features, the function I'm fitting is in higher and higher dimensions. Okay? So how do I do it? Well, again, this will be familiar to most, and the stars mean that you don't have to recreate this derivation, but just know that it's there and understand why it connects to Q-learning. It works something like this. When I make a prediction, there's an actual observation, y. So for each x, there's a right answer, y. And then there's my prediction, which my function produces. And my function isn't going to get everything right. Okay, the difference is called the residual. That's the difference between what I predict, y hat, and what I observe, y. And what I want to do in linear regression, at least kind of standard least squares linear regression, is I'd like to minimize the total squared error, which means I sum up over all the points I, the difference between the right answer yi and the prediction yi hat. Okay? And then I kind of minimize that by choosing my line carefully. Everybody with me? So what is the prediction y hat? Well, we can plug in, okay, this is y hat. I need my... Okay, this is y hat right here. Y hat is the kind of, you can think of this here as exactly the values in the Q function, right? It's a sum over all of the features times the weight. So that's your prediction. And we like to make these things the same. Well, how are we going to do that? We're going to do it by fiddling with the W's. Okay? How do I fiddle with the W's? Well, that's kind of what coordinate ascent is for. So imagine there was only one point. Okay, so you only have one point x. The features are fixed. You've got some target value y, and you've got weights w. And you just like to figure out the values of the weights that minimize this error. So what you do, you write down the error. You would say error is a function of the weights. Okay, and it's the difference, it's the squared difference between the target y and what your feature function computes, right? The sum over k of weights times features. Okay, if there were more points, we'd have to have a sum over points. This is just for one point. All right, well, error is a function of w. I'd like error to be small, so what do? Okay, if I want to figure out how to change component I of the error, and I've got a function of the error, I take derivatives, right? Okay, just calculus. So I take the derivative of the error with respect to a single function. Okay, and I encourage you to kind of go double check my calculus on your own. It's not the kind of thing that's easiest to do on the fly as equations fly by. But what happens? Well, you work that out, and this is the derivative of the error. So if I have a weight vector, and I know for component m, this is the derivative, how do I make the function smaller? I take a step in the direction of the derivative, or in this case, the direction away from the derivative, based on whether I'm want to maximize or minimize. Okay, so that's this. It says you take your current value, and you start with your current value, and you add to it here the negative derivative. Okay, that's why the minus sign has gone away. Okay, how big a step do I take? That's alpha. Right? I know that if I step in the direction away from the derivative, my function is going to go down. I don't know how far to step, right? There's kind of, you can step too far and overshoot, but you take some step size alpha that's reasonably small, and that's going to reduce your error. All right, well, okay, that's this fiddling, right? You fiddle with the w's to reduce your error, and that's the explanation of the Q updates. It says you've got a weight value, and you start with your weight value, and then your kind of error term here shows up, right? The difference between your target, the target that you're supposed to get, at least as far as this analogy goes, is your sample of r plus future value, and your prediction is what your parametric form with all the weights and the features gives you, and you want to make them similar. Okay, so we get exactly this form of the Q update. Any questions on that? Yep. Yep. No, that's a great question, and in fact, you just answered your own question. So the question was, how do we know we can do things well linearly? And the answer is, the features don't have to be these kind of simple linearly independent things. So if you want quadratics, you just make one of your features x squared, and now suddenly it's not a linear thing. That said, with respect to fixed features, these functions that we're going to talk about, and almost everything we're going to do when we talk about machine learning, is then linear. Typically, people incorporate nonlinearity in the features. There are other methods. You can directly learn nonlinear things. It's just, again, the technology isn't quite as hardened. Yes? Yes, is this similar to gradient descent? This is absolutely gradient descent, right? We computed the gradient, right? This is one component of the gradient, and this is a kind of simple gradient descent update. That is all that is going on here is gradient descent. Yes, in the back. How about dependent variables? Are you talking about the other data points, or if the kind of w's are not independent? Yeah, so if the w's, so you mean dependence in terms of kind of significant second derivative information, right? Anytime you're optimizing, there's a whole family of methods you can use, and you can bring all of those things to bear. In this simple technique, which will work if the step size is small enough, you ignore that, right? You don't exploit any information you may or may not know about the second derivative. There are other ways of doing this that bring in more machinery and maybe work better as optimization, but this is the kind of core simplest one. Other questions? Okay, so there's an explanation. The key thing that's easy to forget, given that there's all these equations, is remember we talked about regression as being trying to get the approximation, which is the approximate Q function with features and weights. You want the approximation to approach the target. What's the target, right? The target is just the one-step look ahead, and that's not right either, right? The target is just a single sample. But we're taking such a small step, right? Alpha is small. We take such a small step that the fact that it wasn't really the right target is fine, because the next update is to a different target. And so there is some more subtlety to show that this is going to do the right thing, given that it's not just a linear regression. But this is the kind of core of the connection. Okay, Now, here's another lesson we can take that we're going to see in great detail when we talk about machine learning, but we can already see it. So let's say we were doing regression here, right? And I wanted to do linear regression. So what I might do is I might say, all right, well, X is going to be one feature, and then there might be a constant term called a bias in machine learning, or an intercept term. And then what would I do? I would get a fit that was like this. Okay? And you might say, well, here's exactly the case where you don't want a linear function because it looks like maybe it's a quadratic. So what I can do is I can add another feature, which is x squared. And now if I have linear combinations of 1, x, and x squared, I can build any quadratic I want. So I can learn this, right? Now you say, okay, well, that's great. You're fitting it well. Bring in x cubed. Bring in x to the fourth, right? And what happens if I bring in kind of x to the first all the way up to x to the 15th and I do a regression? What's going to happen? I should be able to fit my data, right? Should we do it? What do you think the fit looks like if I fit a 15-degree polynomial to this data? Okay, I can fit my data, but it's kind of bad news, right? Okay, so the reason why we don't want to kind of fit the data is because we actually don't care about our noisy data, right? What we care about is getting the underlying pattern in a way that's going to generalize. Okay, and this 15-degree polynomial compared to maybe the quadratic one, it may fit the data better, but it looks like it's going to generalize worse. And so you might immediately wonder, how are we ever going to get a grip on how well it's going to generalize versus how well it fits your data? Because the obvious thing to do is fit the data you have. And this is basically machine learning in a nutshell, as we'll see in the kind of last third of the class. Machine learning is about fitting your data without overfitting your data. So you want to learn from your data the stuff that will generalize, but not kind of do a crazy job in areas that you haven't seen here. Okay, so if you give a 15-degree polynomial, right, that's like taking this guy and saying, just like connect my dots. You don't care about connecting your dots. You care about the pattern that underlies them and that will predict the dots you haven't seen. Okay, so that's really the trick. And we'll see a little bit about this now, which is basically don't have a billion features and expect to avoid all overfitting. But really, we're going to start to answer this question in the last third of the course when we talk about machine learning and generalization. Okay. One other thing I want to talk about really quickly, which is policy search. And the reason I want to talk about this is because a lot of high-profile machine learning actually does policy search. We're not going to talk about it in detail. But there's a couple key issues I want you to know. Okay, so what's policy search like? Policy search, instead of trying to come up with values, right? Q-learning, any of these methods we talked about, fundamentally they learn values. How do you act? Well, you've learned Q values, and now you say whichever action has the highest Q value is the one I want to take. So the policies are secondary. Policy search methods directly try to figure out which policies are good, and they don't care whether you have a good approximation of the Q value. Okay, so the problem is that if you create a feature-based representation, usually they can work pretty well. So think back to your project 2 when you came up with some feature-based representation for minimax. And you hand assign some values. You're like, okay, 30 times the distance to the ghost minus 20 times, right? And you just made these numbers up and you tweaked them and eventually it worked great. What are the chances that if I evaluated your function, it was actually the score of the game, right? Like, no way, right? And what that means is you had a function that was very good at distinguishing between actions, but very bad in terms of actually predicting Q values, right? And so in that case, it turns out there's a trade-off, right? Q-learning's priority is actually to get the Q values close. Even if they're not relatively correct, they're kind of all in the right order of magnitude. You don't care about that. All you care about for action selection is that when you look at the Q values from a state, that they be in the right order. They could all be off by a factor of 30. That doesn't matter. And these two things, you might think they go together. You might think, well, if you get the values right, you'll get the ordering right. And if everything's perfect, that's correct. But in practice, there's always a trade-off. You can spend your modeling power, you can spend your data essentially modeling, trying to get the Q values right, or doing prediction, trying to order them correctly. And because these aren't the same, and we'll see this again with machine learning more generally, we need to choose between them. So policy search takes the attitude that we should learn policies that give us good rewards, not learn values that predict those rewards. Okay, so here's a way to do policy search. Totally simple, right? There are many complicated versions of policy search. This isn't it. Policy search says start with a mediocre solution, like run Q-learning, there's your policy. Then, once you've got your feature weights, fine-tune by hill climbing on the feature weights. So nudge feature weight up once, so nudge feature 1 up a little bit, and run a whole bunch of games and see if you get a higher score. Who cares whether the Q values got better? Just see whether or not this new policy gives you higher scores. Okay, now try feature 2, lower it a little bit, see if you get a higher score. And if you think about this, sooner or later you'll start to improve your policy, but you're going to have to run a lot of trials in the process. But that's basically policy search. So now you have a policy search, you nudge the weights up and down, and you see if your policy is better. Now, when you see if your policy is better, how many episodes do you have to run before you have a definitive answer? Because every time you run a policy, it's random. So now we get into kind of sampling statistics and things like that. I'm not going to talk about them, but you can imagine how it works. You kind of have to run a whole bunch of episodes until the error bars on your average return shrink enough that you can tell whether or not the experiment was successful, right? Same ideas behind significance testing. You just need a lot of data points before you know. So in practice, that can be impractical, either because you have to run these so long to figure out whether your nudge was successful, or because there's so many features that it's just going to take you forever to do them one by one. So there are better methods that try to couple the features or somehow avoid having to do so many trials, things that work in different ways, but that's kind of the basic idea, right? You can do a lot of smart things, but at the core, policy search is about directly exploring the interaction between your parameters and your returns. Any questions? Okay, I'm going to show you a cool thing. So Peter will talk later in the semester a little bit more about some of his work with helicopters. Helicopters are interesting because unlike a kind of an airplane where things are fundamentally stable, meaning if you kind of just like if you don't do anything, it'll kind of just keep going, at least at some kind of small scale. Helicopters aren't like that. If you just kind of like take your hand off the wheel, they go unstable very, very quickly. Okay, and so it's very hard to get helicopters controlled in an automatic way. It's hard to pilot them as for humans, and so this helicopter you see, it's not that small, but it's definitely not a life-size helicopter. It's a little model helicopter, and it's very hard to get these things to hover. Okay, you might not think hovering is hard. It's very hard. It's not like getting an airplane to glide. Okay, it's very hard to get helicopters to hover. So here is policy search resulting in a hover behavior for a helicopter. Okay, so what they basically did is they simulated this, they got some approximate policy, and then they kind of kept nudging the weights until it's hovering successfully. All right, so let's see it hovering. It turns out not only are you hovering, it's hard enough to back. I would not recommend the helicopter doing this. This is even harder to do. Okay, you can question whether or not you want your helicopters to be hovering upside down, but it's very hard to do, and this is a case where policy search really let you do something amazing by starting with something decent and tweaking it until kind of the performance you were getting was good. Okay, so we're not only done with today, we're actually done with part 1 of this. So up till now, we've been talking about search and planning and basic kinds of learning, and we've seen how AI methods do a whole bunch of things. Search, CSPs, games, MDPs into reinforcement learning. This was all really fundamentally about choosing actions. Okay, the next part of the course is about uncertainty and learning, and we'll start with that in the next lecture when we start talking about probability and probabilistic modeling.